The Androscoggin River corridor in western Maine had shaped itself around industrial logic. Mills stood at intervals along the water. Warehouses flanked the rail lines. Storage buildings spread across the flatlands between Berlin, New Hampshire, and Lewiston, Maine. The architecture reflected function. Long spans, flat roofs, steel trusses over open floor plans designed for workflow, not weather. Winter arrived in November 1971 as it always did. Snow fell. Roads were plowed. Mills operated. The valley had seen deeper snows, longer cold snaps, heavier single storms. This winter began unremarkably. By December, accumulation was routine. 12 inches, then 18. Temperatures dropped and held. The snow that fell in early December remained in place through Christmas. No January thaw arrived. February brought more snow. March continued the pattern. The buildings absorbed the load silently. Trusses flexed within tolerance. Roof membranes settled under weight. Inside, work continued under flat industrial ceilings, beneath steel beams that had supported summer heat and autumn rain and every previous winter's burden. No one marked the transition from normal winter to structural threat. Snow depth on the ground exceeded 40 inches in many locations by late February. On roofs, where wind could redistribute load and compaction occurred without disturbance, the accumulation reached different figures. Measurement was difficult. Access was limited. The snow was simply present, white and continuous, across every horizontal surface in the valley. The storms that built the problem were not individually notable. 6 inches, then 8, then 5. Spacing irregular. No single event. Just weather proceeding through a season that declined to release what it had deposited. The absence of thaw became the defining characteristic. Temperatures remained below freezing through most of December and January. Brief warming periods in early February produced surface melt that refroze overnight, creating ice lenses within the snowpack. These layers prevented drainage and added density. Normal winter progression in the region included periodic warming, rain on snow, consolidation and reduction. The 1971-1972 season withheld this cycle. Each storm added to existing depth. Compaction occurred through the weight of new snow pressing old snow into denser layers, but total mass continued to increase. By mid-February, snow depths across the valley exceeded historical averages by 20 to 30%. The snowpack was not record-breaking in depth alone. Its persistence was the anomaly. The continuous cold preserved every inch that fell. Meteorological records from Berlin and Lewiston show the pattern clearly. Temperature departures from normal, precipitation frequency, snow water equivalent rising week by week without interruption. The data documented accumulation as a process, not an event. Residents noted the duration more than the severity. Snowbanks narrowed roads for months. Parking lots became corridors between piled snow. Flat surfaces disappeared beneath uniform white. The landscape compressed vertically as snow consumed the space between ground and sky. Buildings became less distinct. Roof lines softened under accumulation. Edges blurred. The architecture simplified into geometric forms under white cover, the details of construction hidden beneath several feet of compressed snow that pressed downward with increasing force as February moved toward March, and the calendar advanced without relief. Snow load calculations begin with snow water equivalent, the depth of water that would result if the snowpack melted completely. Fresh snow might contain 10 parts air to 1 part water. Settled snow compacts to 5 to 1, then less. Ice contributes its full mass. The visible depth of snow provides incomplete information about the weight it represents. In the Androscoggin Valley through late winter 1972, the snowpack evolved toward higher density. New snow fell onto old snow. The lower layers compressed under the weight of upper layers. Time and pressure reduced air spaces. Meltwater from brief warming periods percolated downward and refroze, adding solid ice mass to the matrix. Engineers calculate snow load in pounds per square foot. A foot of fresh snow might weigh 5 pounds per square foot. The same snow, aged and compressed, could weigh 15. Add rain or freezing rain, and the figure increases further. The load accumulates vertically but distributes horizontally across the entire roof surface. Most building occupants never consider the weight above them. Roof structure remains hidden above ceilings. Snow accumulation occurs gradually. There is no sudden burden, only the slow addition of mass over weeks. A warehouse roof spanning 10,000 square feet, bearing 2 feet of dense snow at 20 pounds per square foot, carries 200,000 pounds, 100 tons, distributed across its beams and trusses. The buildings in the valley bore this load without visible warning through February. Steel trusses flexed, connections stressed, roof membranes sagged slightly between supports. These changes occurred in fractions of inches, imperceptible from below, within the normal deflection ranges engineers anticipate. The weight was real, measurable, and increasing, but it was also invisible, silent, and distributed across every flat surface in the valley. The snow did not announce its mass. It simply remained in place, growing heavier as winter refused to release its hold. Industrial buildings in the Androscoggin Valley employed flat roof designs for practical reasons. Flat roofs maximized interior volume. They simplified construction. They reduced wind load. They allowed for rooftop mechanical equipment installation. The slight pitch designed into these roofs, typically 1/4 inch per foot, served drainage purposes but did not significantly shed snow. The structural systems varied by building age and function. Older mills used heavy timber construction, large dimensional lumber beams spaced at intervals, supporting plank decking. Warehouses from the 1950s and 1960s employed steel bar joists or open-web trusses spanning between columns, with corrugated metal decking and built-up roofing membranes. Some newer structures used glued laminated timber beams. All these systems shared a common design assumption: the snow load they would encounter in a typical Maine winter. Building codes in effect during the construction period specified design loads based on historical weather data and engineering judgment. These specifications included safety factors, but the factors applied to anticipated conditions. The flat geometry created two problems under persistent snow accumulation. First, snow remained in place rather than sliding off, as it might on a steep pitch. Second, flat roofs provided no visual indication of load from ground level. A peaked roof shows snow depth clearly along its slope. A flat roof hides its burden behind a parapet or facade. Drainage systems on flat roofs, scuppers, internal drains, gutters, functioned only when temperatures allowed meltwater to flow. In sustained freezing conditions, these systems became irrelevant. Snow accumulated as a solid mass. When brief warming did occur, meltwater could not escape through frozen drains. It pooled on the roof surface and refroze, adding ice load to snow load. The engineering of these roofs was not flawed by the standards of their time. The designs met code requirements, but codes reflected historical experience, and the winter of 1971-1972 was quietly exceeding that experience across the valley, 1 inch of snow at a time. Snow load failure does not typically occur during active snowfall. The critical moment arrives later, after storms have passed and accumulation has settled into its densest state. This delayed failure pattern characterized the events in the Androscoggin Valley. The last significant snowfall in the affected area occurred in the first week of March 1972. Storms then tracked north of the region, but the snow that had fallen remained in place. Daytime temperatures rose slightly but not enough to initiate substantial melting. Nighttime refreezing continued. The snowpack entered a phase of maximum density, aged, compressed, ice-laden, and inert. Buildings that had carried the load through active winter weather now bore the full accumulated weight without the dynamic variability of ongoing storms. The load became static. Structural elements that had flexed under variable conditions now sustained constant maximum stress. Roof trusses experience loading through the connections at joints where multiple members meet. These connections, bolted, welded, or fastened with metal plates, must transfer forces between members. Under prolonged loading, small movements can occur. Fasteners can shift in their holes. Welds can develop microfractures. Wood can compress at bearing points. The first failures occurred not in the buildings with the deepest snow, but in buildings where structural conditions intersected with load conditions. A warehouse with a slightly weaker truss. A mill with a roof section that had been modified years earlier. A storage building where connection details represented older practice. These failures began in the second week of March. They occurred overnight or during early morning hours when temperatures were lowest and material brittleness was greatest. There were no storms, no winds, no dramatic weather. Just the accumulated weight of a winter that had not released its hold, pressing downward until something gave way. The collapses were heard as groaning, cracking, then sudden reports as members failed. In unoccupied buildings, they went unwitnessed until morning. In operating facilities, workers evacuated. The roofs came down onto empty floors, sometimes completely, sometimes in progressive sections, folding inward under their burden. The first confirmed collapse occurred on March 11, 1972, at a paper storage warehouse in Maine. The building was unoccupied at the time of failure, which happened at approximately 3:00 a.m. The roof section that collapsed measured roughly 80 feet by 120 feet. Steel bar joists failed at multiple points. The roof deck and snow load, estimated later at 35 pounds per square foot, fell into the interior storage area, destroying stored rolls of paper and damaging machinery below. The failure mode was progressive. Initial failure of one or two joists redistributed load to adjacent members, which then failed in sequence. The collapse took several seconds but was complete. The building's walls remained standing. The roof lay in a mass of twisted steel, decking, insulation, membrane, and compressed snow on the warehouse floor. Over the following week, additional failures occurred at locations across the valley. A textile mill storage building in Livermore Falls lost a roof section on March 13. A lumber warehouse in Rumford experienced partial collapse on March 15. A commercial cold storage facility in Berlin, New Hampshire, just across the state line in the same watershed, failed on March 16. These events shared characteristics: flat roofs, industrial construction, snow loads exceeding 25 pounds per square foot, and failure during nighttime hours when temperatures were lowest. None of the collapses occurred during snowfall. All happened after the weather had stabilized into a pattern of cold nights and marginally warmer days. Structural engineers called to examine the failures noted similar patterns. Connections had failed, often at welded joints or bolted intersections. In some cases, members themselves had buckled or fractured. The failures were mechanical and predictable given sufficient load. The unusual factor was not how the roofs failed, but that conditions had persisted long enough to bring multiple buildings to failure within a short time span. No fatalities were immediately associated with the collapses. Most occurred in storage or warehouse spaces that were unoccupied. The timing, nighttime, meant that even buildings with daytime workers were empty. The damage was to property and equipment. The broader impact was the realization that more buildings remained at risk, still bearing the same load that had brought down the first structures. After the initial collapses, questions arose about the safety of similar buildings throughout the region. Industrial facilities, commercial warehouses, public buildings with flat roofs, all carried the same snow load that had caused the documented failures. But determining which buildings were at risk required inspection, and inspection presented immediate difficulties. Accessing roofs in winter conditions was hazardous. Snow depth made footing unstable. Ice created slip risks. The act of walking on a roof potentially loaded beyond its capacity added human weight to an already critical situation. Inspection from the ground provided limited information. Interior examination could reveal distress signs, cracking in walls or ceilings, sagging roof decks, doors that no longer closed properly, but these signs might not appear until failure was imminent. Structural engineers in the region were few relative to the number of buildings requiring evaluation. Each inspection required time. Load calculations needed to account for actual snow depth and density, which varied by location and roof configuration. Historical building records were incomplete. Many older structures had been modified over the years without updated documentation of their structural capacity. Building owners faced difficult decisions without complete information. Closing a facility preemptively protected occupants but imposed economic costs. Continuing operations risked catastrophic failure. Insurance considerations complicated the calculus. Coverage for collapse might differ from coverage for closure-related losses. Municipal authorities lacked clear protocols for this type of emergency. Building inspection departments were equipped to evaluate fire safety or code compliance, not to perform emergency structural assessments across entire industrial districts. State engineering resources were limited. Federal disaster declarations applied to storm damage, not to delayed structural failures from accumulated load. The inspection process began with prioritization. Buildings with known structural concerns, older buildings, buildings with longer roof spans, and buildings where occupancy posed higher risk received earlier attention. But this approach left many structures uninspected as March continued, and the snow remained in place. The underlying problem persisted. Until significant snowmelt occurred, the load on every flat roof in the valley remained near its seasonal maximum. Each day without failure did not guarantee safety. It simply meant the structures had not yet reached their limit. After the initial collapses, questions arose about the safety of similar buildings throughout the region. Industrial facilities, commercial warehouses, public buildings with flat roofs, all carried the same snow load that had caused the documented failures. But determining which buildings were at risk required inspection, and inspection presented immediate difficulties. Accessing roofs in winter conditions was hazardous. Snow depth made footing unstable. Ice created slip risks. The act of walking on a roof potentially loaded beyond its capacity added human weight to an already critical situation. Inspection from the ground provided limited information. Interior examination could reveal distress signs, cracking in walls or ceilings, sagging roof decks, doors that no longer closed properly, but these signs might not appear until failure was imminent. Structural engineers in the region were few relative to the number of buildings requiring evaluation. Each inspection required time. Load calculations needed to account for actual snow depth and density, which varied by location and roof configuration. Historical building records were incomplete. Many older structures had been modified over the years without updated documentation of their structural capacity. Building owners faced difficult decisions without complete information. Closing a facility preemptively protected occupants but imposed economic costs. Continuing operations risked catastrophic failure. Insurance considerations complicated the calculus. Coverage for collapse might differ from coverage for closure-related losses. Municipal authorities lacked clear protocols for this type of emergency. Building inspection departments were equipped to evaluate fire safety or code compliance, not to perform emergency structural assessments across entire industrial districts. State engineering resources were limited. Federal disaster declarations applied to storm damage, not to delayed structural failures from accumulated load. The inspection process began with prioritization. Buildings with known structural concerns, older buildings, buildings with longer roof spans, and buildings where occupancy posed higher risk received earlier attention. But this approach left many structures uninspected as March continued, and the snow remained in place. The underlying problem persisted. Until significant snowmelt occurred, the load on every flat roof in the valley remained near its seasonal maximum. Each day without failure did not guarantee safety. It simply meant the structures had not yet reached their limit. As inspections proceeded and failures continued, building closures increased across the Androscoggin Valley. Some closures were mandatory, ordered by municipal authorities after engineering assessments identified imminent hazard. Others were voluntary, made by owners choosing caution over continued operation. The economic effects cascaded through connected systems. A closed warehouse disrupted supply chains. A closed mill idled workers. A closed public building, a school gymnasium, a municipal garage, forced activity relocation or cancellation. The impacts were not dramatic in the way of a single catastrophic event, but cumulative and persistent. Manufacturing facilities faced particularly complex decisions. Shutting down industrial processes could not happen instantly. Equipment required proper shutdown sequences. Materials in process had to be secured or removed. Restart after closure incurred additional costs and delays. For continuous process facilities like paper mills, shutdown meant days or weeks of lost production. Retailers and commercial operations dealt with access problems. Even if a building structure was sound, if snow load made access unsafe, the business could not function. Parking lots buried under snow, loading docks inaccessible, delivery impossible. These conditions persisted as long as the snow remained. Public facilities closure strained communities. Schools moved activities to buildings with pitched roofs or adequate load margins. Emergency services relocated equipment from vulnerable structures. Libraries closed reading rooms. Municipal offices operated at reduced capacity from temporary locations. The closures lasted not days but weeks. Each building that reopened did so only after snow removal from its roof or after engineering assessment confirmed adequate structural margin. The process was slow. The backlog of buildings awaiting inspection or snow removal grew faster than the capacity to address it. By late March, significant portions of the valley's industrial and commercial infrastructure operated at reduced capacity or not at all. The region had not been struck by a disaster in the conventional sense. It had been incrementally disabled by the accumulated weight of a winter that refused to end, bearing down on structures designed for typical conditions, slowly overwhelming the valley's capacity to function normally. Removing snow from roofs became the primary mitigation strategy, but the work was slow, dangerous, and limited by available resources. The task required workers to access and operate on surfaces that might fail under their weight. The snow being removed was dense, ice-laden, and heavy. Equipment options were limited. Hand removal, shoveling, was the safest method for workers but the slowest. Crews worked in small teams, tied off with safety lines, removing snow in sections and pushing it to roof edges where it fell to the ground or into dumpsters below. A crew of 4 might clear a few thousand square feet per day. The valley had millions of square feet of flat roof surface requiring attention. Mechanical equipment could accelerate the work but posed greater risks. Small machines, snow blowers, compact loaders, could operate on roofs if the structure could support their weight plus the existing snow load. Determining this required engineering judgment for each building. Heavier equipment was not viable. The snow had to be moved by methods that did not exceed the very load capacity that was already in question. Melting snow on roofs using heat was considered but rarely implemented. The equipment required, industrial heaters, steam lines, was not readily available. The energy costs were substantial. The meltwater created new problems if drainage systems were frozen. The method was inefficient compared to physical removal. Priority systems developed. Buildings with occupants received attention before unoccupied storage structures. Public buildings took precedence over commercial facilities. Structures with identified distress signs moved to the front of the queue, but the queue was long, and it grew as more buildings were inspected and added to the list. The work continued through March and into April. Contractors from across New England brought crews to the valley. Labor costs were high. Building owners weighed the expense of snow removal against the risk of collapse and the cost of reconstruction. Insurance adjusters became involved in determining liability and coverage for removal costs. The removed snow created secondary problems. Piles at ground level narrowed access routes. Meltwater from the piles overwhelmed drainage systems. The sheer volume of snow meant it could not simply disappear. It had to be relocated, and space was limited. The work was necessary and unavoidable. It proceeded at the pace that safety and capacity allowed. Each roof cleared reduced risk, but hundreds remained loaded beyond design limits as the calendar moved into spring. Building codes in effect during the construction of most Androscoggin Valley industrial structures specified snow loads based on regional climate data and engineering practice of the time. For western Maine, typical code-specified design loads ranged from 20 to 30 pounds per square foot for flat roofs, depending on the specific code edition and local amendments in effect when permits were issued. These specifications included implicit safety factors. Actual snow loads were expected to sometimes exceed design values, but the structural design incorporated margin to accommodate occasional exceedance. The system worked when variations remained within anticipated ranges and durations. The 1971-1972 winter snow loads exceeded design values by margins that consumed the safety factors. Measurements taken during snow removal operations found loads of 35 to 45 pounds per square foot on many flat roofs. Some locations recorded higher figures. The duration of loading, months rather than days, eliminated the time-based safety margin inherent in design codes, which anticipated that peak loads would be temporary. Older buildings, constructed before uniform code adoption or built to earlier standards, operated under different assumptions. Some mills dated to the early 20th century, designed when snow load calculations were less formalized. These structures had survived decades of winters, but survival of historical weather did not guarantee capacity for unprecedented accumulation. The code system was not fundamentally flawed. It was based on statistical analysis of weather data and engineering judgment about acceptable risk levels. But statistical systems define normal ranges, not absolute limits. The 1971-1972 season fell outside the normal range that had informed the code specifications. Engineering investigations after the failures focused on whether code revisions were necessary. The consensus emerged that design loads in the region should increase. Some proposals suggested raising specified loads to 35 or 40 pounds per square foot. Others recommended more sophisticated analysis that accounted for snow density variation, duration of loading, and drift effects. Existing buildings posed a separate problem. Code changes would apply to new construction, but thousands of structures built under older standards would remain in service. Retrofitting them was economically prohibitive in most cases. The practical response was improved monitoring during heavy snow seasons and more aggressive snow removal policies. The failures of March 1972 demonstrated that the relationship between code specifications and actual performance included uncertainty. Design codes reflected knowledge and experience up to a point in time. When conditions exceeded that experience, the codes provided less protection than their prescriptive certainty implied. The direct structural damage, collapsed roofs, failed trusses, destroyed roof membranes, was visible and immediate. The secondary damage emerged more slowly and proved costly in different ways. Water damage was extensive. When roofs failed, they breached the building envelope. The snow that had caused the collapse melted inside heated buildings, producing thousands of gallons of water. Insulation became saturated. Electrical systems shorted. Stored materials absorbed moisture. Equipment corroded. The water damage often exceeded the cost of structural repair. In buildings that did not collapse but experienced significant deflection or cracking, the compromised envelope allowed water and air infiltration. Even small openings admitted wind-driven snow. Freeze-thaw cycles in the damaged areas accelerated deterioration. What began as a minor crack in March became a major repair problem by April. Stored inventory losses varied by facility. Paper products, textiles, and any moisture-sensitive materials were ruined by exposure or by water from melting snow. Finished goods awaiting shipment were destroyed. Raw materials stockpiled in warehouses became unusable. For businesses operating on thin margins, these inventory losses threatened viability. Equipment damage was case-specific. Manufacturing machinery could survive if covered or protected. Precision equipment, printing presses, electronic systems, calibrated instruments, did not. The cost to replace or repair this equipment, combined with business interruption during repair, created financial burdens that insurance coverage might not fully address. Utilities within buildings suffered impact. Roof collapse often damaged or destroyed HVAC systems, electrical distribution panels, plumbing, and fire suppression systems. Even in buildings that did not collapse, the extended closure meant systems were shut down, and restart required inspection and sometimes repair or replacement of components that had frozen or deteriorated. The secondary damage extended the timeline of recovery. A building might be structurally repaired within weeks, but drying out water damage, replacing electrical systems, restoring utilities, and remediating mold growth took months. Some facilities did not reopen until late summer or fall 1972. The comprehensive cost of the 1972 snow load failures, structural repair, secondary damage, lost inventory, equipment replacement, business interruption, and remediation exceeded initial estimates by significant margins. The snow had caused the failures, but the consequences multiplied through interconnected building systems and economic dependencies. The thaw, when it arrived, was uneven and slow. Daytime temperatures in early April rose above freezing with increasing frequency. Nighttime temperatures remained below freezing. The pattern created melt-freeze cycles that complicated rather than resolved the snow load problem. Surface snow melted during the day. The meltwater percolated downward through the snowpack. When it reached frozen lower layers or the roof surface itself, it could not drain through frozen scuppers or blocked gutters. It pooled, then refroze at night, creating ice layers. This process temporarily increased roof loads even as visible snow depth decreased. The snowpack melted from the top down and from edges inward. Roof perimeters, receiving more sun and heat loss from the building below, cleared faster than central roof areas. Parapets and projections created shaded zones where snow persisted. The uneven melting created uneven loading, with remaining snow concentrated in specific roof areas rather than distributed uniformly. Drainage systems thawed gradually. South-facing scuppers and drains cleared first. North-facing or shaded drains remained frozen longer. When drains did open, they often could not handle the volume of meltwater from large roof areas. Overflow created temporary ponding, which added weight until the water eventually found its way off the roof. The thaw progressed through April. By mid-month, most low-elevation roofs in the valley had cleared significantly. Higher elevations and shaded locations retained snow into May. The process was visible: gray, diminishing snow piles, darkening roof surfaces, streams of meltwater running from scuppers, and gradually emerging roof lines. For buildings that had survived the winter under load, the thaw brought relief but also uncertainty. As snow melted unevenly, load distribution changed. A roof that had carried uniform load might now support concentrated load in remaining snow areas. Engineers could not definitively declare a building safe until the roof was clear, and inspection could assess any damage sustained during the loading period. The meltwater itself created issues at ground level. Storm drains and catch basins, still partially frozen or blocked with ice, could not handle the volume. Parking lots flooded. Low-lying areas became ponds. The water eventually subsided as drainage systems thawed and capacity caught up with melt volume. The thaw was not a single moment but a transition spanning weeks. The threat diminished gradually, with each warm day reducing load and each cold night creating temporary setbacks. Spring arrived not as a clear break from winter, but as an incremental release from the accumulated weight that had defined the season. Final damage assessments compiled through spring and summer 1972 documented the extent of the snow load failures across the Androscoggin Valley. The figures represented verified losses, structural failures, repair costs, business interruption, and secondary damage. 23 buildings experienced complete or partial roof collapse between March 11 and April 5, 1972. These ranged from small storage structures to large industrial buildings. The combined roof area lost to collapse exceeded 200,000 square feet. Reconstruction costs for structural repairs alone exceeded $2 million, a significant sum in 1972 currency. An additional 57 buildings were closed for emergency snow removal or structural inspection, and were found to have sustained damage, cracked trusses, failed connections, deflected beams, that required repair before reoccupation. These repairs added to the total cost without involving complete collapse. Business interruption losses were harder to quantify but substantial. Mills operating on multi-shift schedules lost weeks of production. Warehouses closed for inspection could not fulfill orders. Retail establishments lost spring revenue. The economic ripple extended through supply chains and employment. Insurance claims reflected the financial impact. Property insurers faced claims for structural damage, contents loss, and business interruption. Disputes arose over coverage details, whether slow accumulation constituted a single occurrence or multiple events, whether snow removal costs were covered, whether business interruption required physical damage, or if closure for safety reasons triggered coverage. Municipal costs included emergency response, inspection services contracted from outside the area, coordination of snow removal efforts, and repairs to public buildings. These costs stressed local government budgets that had not anticipated extraordinary winter-related expenditures. No fatalities or serious injuries were directly attributed to the roof failures. This outcome reflected the timing of collapses during unoccupied hours and the effectiveness of closures once the risk was recognized. The absence of casualties did not diminish the significance of the structural failures, but did mean the disaster was measured primarily in economic rather than human terms. The total comprehensive cost of the 1972 Androscoggin Valley snow load event, including all direct and indirect damages, was estimated by regional economic analyses to exceed $10 million. This figure accounted for repair, replacement, lost business, and extended effects through the affected industrial sector. The accounting provided a baseline for understanding what had occurred. The numbers documented a winter that had exceeded assumptions and caused widespread structural failure through persistent loading rather than single catastrophic storm. The failures prompted examination of how snow load was understood and codified in building design. Engineers, code officials, and researchers analyzed the 1972 event to determine whether revisions to standards were warranted and what form those revisions should take. The analysis confirmed that the problem was not design error but exceedance of design assumptions. The buildings that failed were not poorly constructed. They were subjected to conditions beyond what their design anticipated. This distinction mattered because it directed the response toward updating assumptions rather than attributing fault. Snow load in building codes reflects statistical analysis of historical weather data. The codes specify loads that have a defined probability of exceedance, typically a 50-year return period, meaning a load with a 2% chance of being exceeded in any given year. The 1971–1972 winter conditions in the Androscoggin Valley fell beyond this probability envelope. Code revisions adopted in Maine and New Hampshire in the mid-1970s increased specified snow loads for flat roofs in the region. The increases ranged from 5 to 10 pounds per square foot, depending on specific location and roof configuration. The revisions also included more detailed treatment of snow density, drift accumulation, and rain-on-snow loading scenarios. Design guidance also evolved to emphasize the importance of drainage and to specify requirements for snow removal access. Roofs were increasingly designed with consideration for how snow would be removed if accumulation approached critical levels. Provisions for attachment points for safety equipment became more common. The concept of load duration received greater attention. Engineers recognized that sustained loading, even at moderate levels, could lead to time-dependent failures through mechanisms like creep in timber or fatigue in connections. Design methodologies began to account for the difference between short-duration peak loads and prolonged elevated loads. Education of building owners and facility managers included information about snow load monitoring and when to initiate removal. The idea that snow on roofs was a manageable hazard requiring attention, rather than simply an inevitable part of winter, gained traction. Existing building inventory presented ongoing challenges. The thousands of structures built under previous codes remained in service. Retrofitting was rarely economically viable. The practical approach was heightened awareness and active management during heavy snow seasons. The 1972 event became a reference point in structural engineering literature. Case studies examined the failures, load calculations, and code implications. The winter when the roofs gave way entered the knowledge base that informed future design decisions. By June 1972, the Androscoggin Valley had returned to operational status. Collapsed roofs had been rebuilt. Damaged structures had been repaired. Closed facilities had reopened. The snow was gone. The evidence of what had occurred was limited to construction activity and insurance paperwork. The winter left little visible trace. Buildings were restored to match their previous appearance. Roof replacements used modern materials and met updated codes, but from the exterior, the structures looked as they had before. The scars were internal. Replaced trusses, new connections, reinforced members hidden above ceilings where occupants would never see them. The changes were in procedures and awareness rather than landscape. Building departments implemented winter monitoring programs. Facility managers developed snow removal protocols. Engineering firms gained experience in load assessment and emergency evaluation. Insurance policies were revised to clarify coverage for snow-related damage. The statistical record absorbed the winter's data. The 1971–1972 season became a data point in climate records, an outlier that would influence probability calculations for future design loads. Meteorological summaries noted the persistence of cold, the absence of thaw, the accumulation totals. The industrial valley continued its function. Mills operated. Warehouses stored goods. The rail lines moved freight. The buildings sheltered the activities they were built to contain. The roofs held the weight of summer heat and autumn rain and the winters that followed. What changed was not visible from outside. It was in the calculations engineers performed, in the attention building owners paid to snowfall totals, in the recognition that assumptions built into structures were assumptions nonetheless. reflective of experience but not guarantees against conditions that might exceed that experience. The 1972 snow load event was not a storm. It was a season. It did not arrive in a day. It accumulated over months silently, until the weight exceeded capacity and structures failed under burden they were not designed to carry. The valley learned what it had not known before, that winter could disable through persistence, that roofs could fail weeks after snow stopped falling, that the quiet accumulation of load could overwhelm structures designed for normal conditions. The knowledge became part of engineering practice, code specifications, and institutional memory. The winter when the weight became too much, when the roofs gave way, when the snow stayed too long.